Ever wondered if you can add two numbers without using the plus or operators? That's exactly what sum of two integers asks. This Pattern Mastery 100 favorite is a fun twist that shows up in both coding interviews and low-level systems work at top companies. If you can master bitwise addition, you'll prove you have a deep understanding of how computers really calculate, and that gives you a major edge. Let's break it down. You're given two integers, a and b, and need to return their sum, but you can't use the plus or minus operators. You must use bitwise operations like AND, XOR, and shift. Now let's assess. Normally, addition works by summing each bit, carrying over when needed. Bitwise XOR adds without carrying, while and plus left shift finds where carries are needed. The trick is to loop, add with XOR, then carry with AND or shift, until there are no more carries. This simulates how a CPU adds numbers at the bit level. Here's our approach. While b, the carry, is not 0. We use a XOR b to add the bits, without including the carry. Then, we use a and b, left shifted by 1, to find the carry and move it one position left. Next, we update the values of a and b with these new results. Once the carry becomes 0, a holds the final answer. Let's try to implement it using solution 1. This defines a function called getSum that takes two numbers, a and b. Our goal is to add them without using the plus operator. Instead, we'll use bit tricks. This sets up a 32-bit mask. All 32 bits are ones. Think of it like a keep only the last 32 bits filter, so our operations behave like a normal 32-bit integer machine. This stores the largest positive 32-bit signed integer. We'll use it later to decide whether our final result should be treated as positive or negative. This loop runs as long as there's a carry to deal with. Even though it looks like a loop, it's still a one-time, because with 32-bit integers, the carry can only ripple across at most 32 steps. That's a fixed limit. Here we compute the carry bits. A and b finds positions where both have a 1. Those are exactly the spots where addition would produce a carry. Then unmask keeps it locked to 32 bits. Now we compute the sum without carry. XOR, caret, is like adding bits where 1 plus 0 becomes 1, and 1 plus 1 becomes 0, which matches addition except for the carry part. Again we mask to stay in 32-bit mode. This shifts the carry left by 1, because a carry affects the next higher bit in real addition. Then we mask again. After this line, b represents the carry we still need to add back in. This closes the loop. Each pass reduces the remaining carry until there's none left. Now we return the final answer. If a is within the positive signed range, we return it directly. Otherwise, it means the 32-bit result represents a negative number in 2's complement form, so we convert it into the correct negative JavaScript number using tilde a mask. And this closes the function definition. And that's how this algorithm works. It first sets up 32-bit boundaries and constants, then repeatedly combines sum without carry, XOR, with shifted carry bits, and plus left shift, until no carry remains. Efficient, simple, and elegant. Let's test our function using this input. A equals 1 and b equals 2. These values represent the two integers we want to add together, so it's basically asking for 1 plus 2. Inside the function, we add without using the plus sign by using bit operations. XOR, a b, combines bits where they differ, that acts like addition without carrying. And a and b finds where both bits are 1, that creates the carry. Then we shift the carry left and repeat until there's no carry left. For 1 and 2, their binary forms don't overlap in a way that creates a carry, so it quickly resolves to 3. And that's exactly what we get. Output equals 3, which matches the expected equals 3. So the result makes perfect sense. 1 plus 2 equals 3, and our implementation passes the test case cleanly. So, our implementation is correct. The algorithm successfully adds two integers using bitwise operations, efficient and accurate. Now let's try another implement approach using solution 2. Here we're defining a function called getSum that takes two numbers, a and b, and will return their sum, but without using the normal plus operator. Think of it like adding using only bit tools instead of regular math. Time complexity, 1, because we're working within a fixed 32-bit integer range. We create a constant called mask. This is a 32-bit mask where every bit is 1. It's like a keep only the last 32 bits filter, so our results behave like a normal 32-bit computer integer. Next, we define int_max, which is the largest positive 32-bit signed integer. This helps us later decide if a result should be treated as a normal positive number or converted into a negative number using 32-bit rules. Now we define a helper function. This helper does the real work using recursion, meaning it calls itself again and again until the job is done. Here, x acts like the running total, and y acts like the carry we still need to add. This is our stopping point. If y is 0, that means there's no carry left, so we're done adding. But there's a twist. If x is bigger than int_max, it means in 32-bit signed math, that value should actually represent a negative number. So we convert it using bit tricks. $xmask is basically translate this 32-bit value into the correct signed negative result. This is the heart of the algorithm. We split addition into two parts. xy computes the sum without carries. Think, add bits where only one side has a 1. X and y finds where both bits are 1, that's exactly where a carry happens. 1 shifts those carry bits left, because carries affect the next higher bit, and mask keeps everything locked to 32 bits. Then we call helper again with the new partial sum and the new carry. We repeat until carry becomes 0. Still 1 overall due to fixed 32-bit width. This line closes the helper function definition. Our recursive adding machine is now ready. Here we actually start the process by calling helper with the original inputs a and b. The helper will keep combining sum without carry and carry until it finishes. And this final line closes the main getSum function. Done. And that's how this algorithm works. It first sets up 32-bit boundaries and safe limits, then repeatedly adds using XOR for the partial sum and plus shift for the carry until no carry remains. Efficient, simple, and elegant. Let's test our function using this input. A equals 2 and B equals 3. These numbers represent the two integers we want to add together, so we're computing the sum of 2 plus 3. Here's why the solution works. It adds using bit operations instead of the plus sign. XOR combines bits where they differ, that's like adding without carrying. And, then shifting left, finds the carry bits, that's what needs to be added next. For this input, start with x equals 2 and y equals 3. xy gives the partial sum, and x and y, 1 gives the carry. The helper keeps repeating this until y becomes 0, meaning there's no carry left. At that point, the remaining x is the final sum, which should be 5. And that's exactly what our program outputs, 5. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully adds 2 and 3 using bitwise operations without using plus, efficient, accurate, and reliable. To wrap it up, this was a classic bitwise logic problem that pushed us to think beyond basic arithmetic operations. Breakdown recap. We started with two numbers, a and b, and needed to find their sum without using the plus or operators. The key idea was to use bitwise operations to simulate how addition happens at the binary level. Assess recap. We broke it down conceptually. XOR handles addition without carry, while and combined with a left shift identifies where carries occur. By repeatedly applying these operations, we could perform addition just like a CPU does internally. Structure recap. The logic was simple but powerful. Loop until there are no more carries. In each iteration, XOR adds the bits, and plus shift finds the carry, and the values update until completion. Implement recap. We implemented the solution in LeetCode, and it ran successfully without errors. Check recap. After testing with different inputs, the code passed all test cases, confirming that our bitwise approach worked perfectly. The key takeaway? Even something as basic as addition can be reimagined with pure logic. Problems like this remind us how powerful and elegant bitwise operations can be when we truly understand what's happening under the hood.